Thanks for watching my video today. Let's discuss a Ramanujan integral. Then is the integral from 0 to infinity sin n x upon e to the 2 pi x minus 1 dx is 1 upon 2 1 over e to the n minus 1 plus 1 by 2 minus 1 over n, where n is greater than 0. Okay, so if n is equal to 0, then this integral will be a divergent. Okay, it will not converge, so in order to be converged, so n must be greater than 0. So here is my approach, okay, for this Ramanujan integral. So let me call integral to be I. So I is equal to integral from 0 to infinity sin n x upon e to the 2 pi x minus 1 dx. Okay, which is equal to, now I'm going to multiply both numerator and denominator by e to the negative 2 pi x. Then is integral from 0 to infinity sin of n x upon e to the 2 pi x minus 1 into e to the negative 2 pi x upon e to the negative 2 pi x dx. Okay, now multiply them, you will get integral from 0 to infinity sin n x upon, so this and this multiply, so it will be 1, right? So 1 minus, and this one, and 1 is nothing but e to the negative 2 pi x into e to the negative 2 pi x dx. Now I'm going to use the geometric progression, okay, GP. We know that 1 over 1 minus x is nothing but sum from n equal to 0 to infinity x to the n. Okay, use here in place of 1 minus this one, I'm going to use this one. And again, note that this summation is this summation and this integral, I'm going to interchange them. Then is I equal to sum from k equal to 0 to infinity integral from 0 to infinity sin n x into e to the negative 2 pi x, this one, and into x is here, x is nothing but e to the negative 2 pi x, right? X to the n, meaning e to the negative 2 pi kx, right, dx. Actually it will be something like this, e to the negative 2 pi x whole k. Okay, this is nothing but e to the negative 2 pi kx, right? Therefore it is like this. Now this and this they have the same base, so I'm going to combine them. I is equal to sum from k equal to 0 to infinity integral from 0 to infinity sin n x e to the negative, if you see this 2 pi common, right, 2 pi, then k plus 1 and x, right, dx. Now we know that integral from e to the ax sin bx dx is nothing but e to the ax upon a square plus b square a sin bx minus b cos bx. Okay, this one I have already done, so this one you can use integration by part. Okay, integration by part, then you will come out with this. Now here 1 is or a, if you see e to the right, a is nothing but negative 2 pi k plus 1, right? Here a is equal to negative 2 pi k plus 1. This is our a, and our b is nothing but n. Okay, now substitute the value here. I is equal to sum from k equal to 0 to infinity e to the negative 2 pi k plus 1 x upon 2 pi k plus 1 whole square, right, a square, plus b is nothing but n square, and a is nothing but it will be negative. Okay, negative 2 pi k plus 1 sin n x, b is n, okay, minus b, which is n cos n x, and integral from 0 to infinity. Now I is equal to, now if you plug infinity, so e to the negative infinity is, this is just 0. Okay, so meaning this whole term will be 0 for infinity, and for 0, if you put 0, we know that e to the 0 is always 1, so this will be 1, and here sine of 0 is just 0, so this will be cancelled out, and minus cos 0 is 1, right, cos 0, so it will be minus time, right, minus, and minus will be positive, so it will be, we are left with only n. Okay, n upon sum from k equal to 0 to infinity, here n upon this one 4 square 2 square is 4, right, pi square k plus 1 square plus n square. So this is just the same thing as sum from k equal to 1 to infinity n upon 2 pi k whole square plus n square, right, this one. This start from k equal to 0, meaning it will start from k, if you put k, then it will be 1, right, If you put 1, then it will be 2, so it will go on. So then is the same as k from 1 to infinity, right? Now we are going to see this series, okay? One is this series, so we are going to evaluate that one and see what is R. And let's see about the expansion of partial fraction expansion of cone hyperbole of x, okay? Then we have already done cone hyperbole of x is 1 over x plus 2 times sum from k equal to 1 to infinity x upon x square plus pi square k square. If you see here, same thing, right? Pi square is already here, k square already here, we need only 2 square. Here x is nothing but n, okay? So here we need 2, right? We need 2 square, meaning we need 4. So in order to get that, I'm going to put x equal to n by 2, okay? If you put here x equal to n by 2, we have cone hyperbole of n by 2 is equal to 1 upon n by 2 plus 2 sum from k equal to 1 to infinity n upon 2, right? X is n upon 2 and n upon 2 whole square plus pi square k square. Then what you get, cone hyperbole of n by 2 is equal to, this is nothing but 2 by n plus, here 2 square is 4, right? So that 4 will be, if you take the common denominator, then, or LCM you can say, for this two, if you take LCM, 4 will be there, so it will be n square plus and 4, right? 4 is nothing but 2 pi k whole square, and that 4 will be coming out here in the upper, right? And again this 2 and this 2 we will get cancelled. So this is just simple algebraic, okay? I hope you can do that. Now next will be continuation of that one, okay? Now cone hyperbole of n by 2 is equal to 2 by n plus 4 times 1 is this summation. This summation is nothing but sum from k equal to 1 to infinity n upon n square plus 2 pi k whole square. Exactly this one, right? This is nothing but our integral I. So I'm going to substitute in place of this to be I, okay? So what do we have next? Okay, now if you find out I, so 4I is equal to cone hyperbole of n by 2, this transfer there, minus 2 by n. So I will be 1 by 4 cone hyperbole of n by 2 minus 2 by 4n, okay, which is 1 by, which is, this is 2, 2, right? So there will be, here will be 1 by 2 will be left. So 1 by 2 common, so I'm going to take out common 1 by 2 and cone hyperbole of n by 2 upon 2, right? Here taking out 2 common here, I mean 2 is left, minus taking out 2 common here, so 1 upon n. And again, in order to get our integral, actually this is the solution already, okay? This will be the solution, but in order to get our this exact result, so what we do is we have to see the definition of hyperbolic cone, okay? Cone hyperbole of x is nothing but cos hyperbole of x by sin hyperbole of x, which is cos hyperbole of x is 1 by 2 e to the x plus e to the negative x, right? Upon sin hyperbole of x is 1 by 2 e to the x minus e to the negative x. These two get cancelled, then you get e to the x plus e to the negative x upon e to the x minus 1 minus e to the negative x, okay? Here if you put x equal to n by 2, then what do we have? I is equal to 1 by 2 into this 1 by 2 here, 1 by 2. Cone hyperbole of n by 2 is e to the n by 2. X is nothing but n by 2, okay? E to the n by 2 plus e to the negative n by 2 upon e to the n by 2 minus e to the negative n by 2 minus 1 over n. This one, okay? Which is equal to 1 by 2 into e to the n by 2 plus e to the negative n by 2 upon e to the n by 2 minus e to the negative n by 2. Now multiply both numerator and denominator by e to the n by 2, okay? E to the n by 2, e to the n by 2 minus 1 over n. Then what do we have? I is equal to 1 by 2 into 1 by 2. Multiply this and this, then you'll get e to the n, right? Plus multiply this 2, it will be 1 upon e to the n minus 1 minus 1 over n, which is equal to 1 by 2. Now this one we can split it, 1 by 2 into e to the n upon e to the n minus 1 plus 1 by 2, this 1 upon e to the n minus 1 minus 1 over n, right? Now I is equal to 1 by 2 into 1 by 2 of 1 upon e to the n minus 1 plus 1 by 2 this one e to the n, right? Now I'm going to subtract 1 and add 1 again. Okay, negative 1 and plus 1 I'm going to do it. So e to the n minus 1 negative 1 over n. So I is nothing but 1 upon 2 1 into 1 upon 2 into 1 over e to the n minus 1 plus 1 by 2. Now split up this into 2, e to the n minus 1 upon e to the n minus 1 plus 1 by 2 1 upon e to the n minus 1 over n. Okay, so these two are exactly the same, so cancel out. Then what did we left? We left only 1 by 2, right? So I is nothing but 1 by 2, and this one and this one, it will be just 1, right? 1 upon e to the n minus 1 plus 1 by 2 minus 1 over n. Then is exactly our result, right? This is. So this is our result. Therefore, our integral from 0 to infinity sin nx upon e to the 2 pi x minus 1 dx is 1 by 2 into 1 upon e to the n minus 1 plus 1 by 2 minus 1 over n. So this is the proof, hence proof. Okay.